So in the last two videos in this module, I want to cover a somewhat complex topic, but I think it's really important for us to understand it, which is how we get from the waveform representation of digital audio, where we have time on our x-axis and amplitude on our y-axis, to the sonogram representation, where we could see much more information about the frequency and the timbre content of the sound. So we're going to talk about how we get from the waveform to sonogram and the role that the Fourier theorem plays in that. We're going to talk about how we kind of work around the limitations of the Fourier theorem through a process of windowing, periodicization, and fast Fourier transform in order to take kind of any sound that we might want to look at and represent it as a sum of a series of sine waves. And we'll talk about some implications of this algorithm in terms of particularly two parameters of it, frame size and bin width, that we need to think about very carefully as we're configuring it, because they have some serious implications in terms of what we get as a result. So it's pretty obvious, now that we know how sound is represented digitally on a computer, it's pretty obvious how a waveform representation like this comes about. We simply take the successive amplitude values and we kind of plot them over time on the x-axis. And then we have our waveform. We can connect the dots if we want to make it look a little nicer. But how we get from this to that is not obvious, because when we represent sound digitally, we're encoding a series of amplitude values over time. We're not encoding any information about frequency at all. So that's why we need to think about this a little bit more carefully and think about how we get to this. So I want to revisit the Fourier theorem, which we looked at in the timbre video earlier. I want to look at it in a little bit more depth now. Just to recap, we said the Fourier theorem said that any periodic waveform can be represented as the sum of sine waves at frequencies that are integer multiples of a fundamental frequency. And we looked at examples of this with a sawtooth wave, and we looked at examples of the trombone sound, of how we could kind of combine these sine waves together. And we wouldn't hear them anymore as these individual sine waves, but we'd hear them kind of coming together compositely to create this single sound for us. Because of this special relationship they had to each other in terms of being integer multiples of this base frequency, and because of the way that they were linked. At the time, I also mentioned a really important limitation here, this periodic limitation here. This only works for periodic waveforms, like a perfect sine wave or a perfect square wave or something like that. And that isn't how sounds work in the real world, really. They're not perfectly periodic. They don't repeat a cycle infinitely over and over and over again without any variation. So that's one problem. Is that we've gotten this spectra aspect of timbre here, but not the envelope timbre, not the changing in time aspect of it. The other problem here, and this is actually something I didn't write into this text for the Fourier theorem at the time, is that when we say sum of sine waves here, there's an important caveat here. It's a potentially infinite number of sine waves may be required to do this. And computers don't tend to like infinity very much. They're not continuous beings. They're discrete. They do things as sets of zeros and ones. So if we need potentially infinite number of sine waves to do this, that's also going to be really problematic for us. And so what we do instead is we use this basic idea of the Fourier theorem, but we tweak it a little bit. We kind of fake it out, if you will. To pretend that we're working with periodic waves, and we do a process that doesn't do things perfectly, but it doesn't use an infinite number of sine waves either to make this happen. And so there's three stages to this I'm going to talk about in detail. Windowing is when we take a waveform and we split it up into tiny little bits. And then we take each of those tiny little bits and we do something called periodicization. There's really nothing to this. We just pretend that that little bit repeats infinitely, so that it's a periodic sound. And then on each of those little windows, we apply a method called the fast Fourier transform, which you'll often see abbreviated as FFT. And so we apply this process in order to convert our time domain set of amplitude values into information about frequency. So I'm going to go through each of these steps in more detail now. The first step is windowing. So what we do is we divide the audio into equal size overlapping frames. So let me show you what I mean. We pick a number of samples that would be included in each frame. So like our frame size might be 1,024 samples, for instance. So these are tiny frames. So 1,024 samples, if our sampling rate were 44,100 hertz, is about 1/40th of a second in that case. So tiny fractions of a second. And so if we were taking this waveform here and splitting it up, we might have that be one, and then we're going to overlap them with each other. So that might be another, that might be another, that might be another, that might be another, and so on and so forth, all the way through our file. But it's more complicated than this, actually, because these are overlapping and we want smooth transitions from one to the next. As we're doing this, each of them kind of fades in and fades out. So the first one will kind of fade in and fade out with an amplitude envelope like that. And this one will fade in and fade out too. This one will fade in and fade out too, and so on. So there's always one that's kind of fading in and always one that's kind of fading out with an overlap like that, and so on and so forth. So that's what windowing is. We end up with these windows that kind of fade in and fade out that are each tiny fraction of a second long. Then we take each of those windows, and this is the easy part. We pretend that it's a periodic function. So we take this tiny little window here, and we repeat it, 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 and again, and again. And we just pretend that this goes on forever. So now we've met the periodic requirement of the Fourier theorem. And then the final step is called the fast Fourier transform. And the details of how this algorithm works are a little bit beyond the scope of this course. I encourage you to look up some more details if you're interested, and I'll point you towards some references. But right now I just want to explain about kind of pretend that it's a black box and explain kind of what goes in and what comes out. So what comes in are these amplitude samples over time in the frame. So if our frame size is 1,024, we'd have 1,024 amplitude values that would go in. And what would come out are a set of amplitudes and phases for each frequency bin. So in other words, I'm going to divide up my frequency space into a series of linearly spaced bins. And I'll get into more of how this works in a second. And then I'm going to look at what's going on in each of those, how much energy is there in each of those bins, and also what's the phase of the sine wave that's represented by each of those bins. And so there's some simple ways to calculate how the algorithm does this. My number of frequency bins is half of my frame size. And then the width between each of these bins, so we're, from one to the next, is my Nyquist frequency, the highest frequency I can represent at my sampling rate, divided by my number of bins. So let's work through an example here just to make sure this is totally clear. So my frame size is 1,024 samples. And my sampling rate is 44,100 hertz. Then my Nyquist frequency would be 44,100 divided by 2, so 22,050. So then my number of bins is the frame size, 1,024, divided by 2. So that's 512. My bin width is going to be my Nyquist frequency, that's 22,050, and that's hertz, just to be clear. 22,050 divided by my number of bins, 512. This comes out to about 43 hertz. It's a little bit more than 43 hertz. So that means that my frequency bins are going to be spaced at 0, 43, at 86, 129, so on and so forth, all the way up to 22,050 hertz. So that's how this stuff is divided up. And then I have information at that point about what's going on in each of those frequency areas, and so you can see how I could generate a sonogram from there. I could take each of these frames and generate kind of one vertical strip of frequency view in my sonogram based on that data that's coming back. And I'm going to show you how that works in a second. But before I do that, I want to talk about some of the issues with this process, because it's not a perfect process. First of all, it's a lossy process. I lose data in this process. If I do this fast Fourier transform and then I go back to my waveform, I've lost something in the process because I've split these things up into these linear frequency bins. So I only know about what's happening with a fairly low resolution as I'm moving up in frequency. And I also only know things about a fairly low resolution in terms of time, because I only know what's happening frame by frame by frame, so 1,024 samples in the example we've been using at a time. And so there's actually a big trade-off here when I pick my frame size in terms of how much resolution do I want in the time domain versus how much do I want in the frequency domain. If I want to know exactly when things are happening in time along my x-axis, I can pick a very low frame size. So my frames are really tiny, so I get a lot of time resolution horizontally. But then my bin width gets huge, and so I know very little about what's happening vertically in my frequency dimension. If I want to know a lot vertically in my frequency dimension, I can pick a really high frame size, but then there's a lot of time that passes from one frame to the next, and so I lose a lot of resolution in the horizontal and the time domain. I'll show you this in a demo in a second. The one point I wanted to make first, before I go there, is this word here. These bins, the frequency space is divided linearly. But if we remember from our module, our video on psychoacoustics, we actually listen, we actually hear a pitch not linearly but logarithmically. And so a lot of these frequency bins are kind of wasted, if you will, on things very high up in frequency space. So half of the bins are for what we would hear is just the final octave of our frequency space. So this isn't a great match either, but that's how this particular algorithm works. So let me go ahead and open this up in Reaper for you. And what I want to show you, I'm going to play a sound here, and I want to show you the sonogram for it. And we have an option here to pick our frame size. So I'm going to show you how this is going to start looking differently, that time versus frequency resolution trade-off as I pick different frame sizes. So we're at 1024 right now, samples, which is a good compromise. But what if I want really, really, really good frequency resolution? I'm going to go up to 32,768. And you can see how much clearer things are in the vertical dimension now. It's a lot less grainy. I can tell exactly where things are happening vertically in my frequency dimension. But now it's kind of blurred in the horizontal dimension. I don't get a very good sense of the rhythm at all anymore. This is a very rhythmic sample here. So if I went down to something really low, 16, now I'm seeing the rhythm very precisely coming through here. You can see all those peaks representing every single note that's playing, but I see almost nothing to represent what's happening in the vertical dimension. It's all just kind of these bars that are going up more or less the same height as each other. I'm not seeing very much at all about specifically where things are happening in frequency space. So I just wanted to show that to you to illustrate that trade-off, that decision you have to make when you pick the frame size. And that's why pretty much anything that's doing frequency domain analysis is going to give you this option over the frame size, even a commercial music production program like Reaper. So to review, what we talked about here were these limitations of the Fourier theorem that need to work with periodic waveforms, and that there's a potentially infinite number of sine waves required to represent those waveforms. We talked about how to get around that through a process that involved windowing, periodicization, and the fast Fourier transform. And we particularly talked about frame size and bin width as parameters of the fast Fourier transform, and the trade-offs we need to decide about as we're picking a frame size in terms of the time versus frequency resolution. What we're going to talk about in the final video in this module is, now that we've gone from this waveform representation to a frequency representation, what can we do with it? Because we can obviously make a pretty picture, but there's a lot of other things that we can do with this as well.